Welcome. This is Fundamentals of Micro and Nanofabrication. I am Swayam Prabha from IIT Bangalore. Today we shall continue the module on subtractive processing, and specifically we are looking at wet etch. In this lecture we shall go into a little more details of some specific recipes of wet etch, specifically that do anisotropic etches. We will look at some detailed mechanism of H&A etch and try to make some generalizations. So, let us get started. So, the first etch that we shall talk about today is the isotropic silicon etch. It is also colloquially also called H&A etch. The H here stands for hydrofluoric acid, which is this. Then its nitric acid stands for N, which is this, and then of course acetic acid, which is the diluent. The basic mechanism is fairly easy to understand. So, silicon is of course a reduced elemental semiconductor. You first oxidize it using HNO3 to silicon dioxide, and then this silicon dioxide then gets etched with hydrofluoric acid to form a complex that we saw in the last lecture. And acetic acid is simply a solvent to transport the reactants and products away. However, if you look into a little more detail, the H&A is a fairly interesting etch, and the acetic acid does something very special, and that what is that special is something we will discuss, but the hint is you only understand the details of an etch if you consider the etch to be an electrochemical problem. It is not just simple chemistry, it is not just simple dissolution, it is a little bit more complicated, alright. So, this is a concept I hinted at when we took the first lecture on wet etching, where I mentioned that electrochemistry is fairly important. So, randomly on any etched surface you actually form these positive and negative domains, and these positive and negative domains are actually the anode and the cathode where the electrochemistry is happening. Between these positive and negative domains you can imagine will be an electric current, because anytime you have a potential you have current. And because these positive and negative domains are so close to each other, the electrochemical corrosion currents that actually go through this device are fairly high. They can be as high as 100 amps per centimeter square. This is not a device course, but those of you who do have a device background may be able to appreciate that this is a fairly intense amount of current, right. Now, of course, these domains do not remain static. The domains come up because there is a perturbation in the system. They are not there because we are actually putting a voltage or actually putting a current. So, these domains sort of change their polarity, they change their size, they change their direction randomly over the etching process, and that is how the whole film gets etched. Okay. Now, during the H&A etch, if you look into detail at what exactly is happening at an anode or a cathode, you realize that at the anode, you are taking a silicon, and the silicon is losing an electron to form silicon plus, and this electron then gets taken away. And at cathode what is happening is a reduction, where the silicon plus is accepting an electron and forming elemental silicon back. Now, a redox reaction is one in which one species is getting oxidized and a different species is getting reduced, and the both are happening simultaneously. So, the oxidation of silicon is a redox reaction, and and that is a term that we shall come back to in the next slide. So, once again, if this was not clear, the domains are random, and so this equation is these equations are happening randomly over the whole substrate, and at some point a surface is suffering from oxidation, and at a different moment in time it could be suffering from a reduction. Okay. So, what you hope is, if the etch is really uniform, that these two mechanisms will over a long term or over the lifetime of an etch even out, and you will not see any differences, so you will get a smooth film. Of course, if that does not happen, then you start seeing non-uniformities. So, let us continue the journey into understanding the H&A etch into a little more detail. So, we have already discussed that there are these randomly random domains which are acting as anode and cathode, where oxidation and reduction is happening. Now, because silicon is group 4 and it has a valency of 4, the silicon gets oxidized to silicon plus 4, which gives out 4 electrons which get given to the anode. And at the cathode you suffer reduction, where 4 NO2 molecules react with the electron to 4 NO2 minus ions. Now, some of you may ask the question, where is this NO2 coming from? We started with HNO3, not NO2. So, why are we talking about NO2 all of a sudden? The short answer is the NO2 comes from HNO3. How, why, and exactly the mechanism will be discussed in the next slide. But for now, let's just assume there is NO2 in the system and that NO2 is actually getting reduced at the cathode. These two reactions are of course the equal and opposite electrochemical reaction. Then you also have a chemical reaction which is the formation of silicon dioxide. Here these oxidized silicon ion reacts with the hydroxides to form silicon hydroxide, which then dehydrates to form silicon oxide and water. Okay. And this silicon dioxide that has now formed then reacts with the HF as you would expect it to, forming this soluble complex, thereby etching the silicon dioxide and exposing fresh silicon that can once again get oxidized at the anode. So this is how the mechanism continuously goes. So the intuitive understanding of the mechanism that we started with in the first slide was not too off, right? So overall what is happening is that the exposed silicon is getting oxidized with HNO3, specifically NO2, not HNO3, but still because of HNO3's presence is getting oxidized. That silicon dioxide is then reacting with hydrofluoric acid to get etched away. That exposes fresh silicon that can once again react with the HNO3. Of course, the open things that I have still not answered are one, where is this NO2 coming from, and B, what is this special role of acetic acid in this combination. So let us first tackle the presence of NO2. HNO3 is an oxidizing acid, and that a lot of you would know from 12th grade chemistry, but the exact mechanism of how HNO3 actually does the oxidation is a little complex. It turns out it does through NO2, and one of the products that actually gets formed in the HNO3 during this process is HNO2. So for details, let's dive into these set of reactions. So the first reaction here should be obvious to a lot of you. This is simply that HNO3 is a strong acid, which means it really likes to ionize, and if it ionizes, it will form the nitrate ion and the hydrogen ion, and that's simple and easy to understand. But competing with this ionization process is the oxidative ability of HNO3. So HNO3 is also an oxidant, and that is a competing chemical reaction that is happening against this ionization. So it can do the ionization reaction or it can do the oxidation reaction. So what is the oxidation reaction? So these three are the set of oxidation reactions. So let's assume there is a little bit of HNO2 in the system. Once again, you can question where is this HNO2 coming from, but for now let's just assume there is some HNO2 in the HNO3. Maybe it's an impurity, just for argument's sake. So that impurity HNO2 will react with the HNO3, forming two NO2 molecules and water. Okay. Now this is the reaction I have marked in red, because this is what leads to the formation of the NO2, and by and large this is the step that is the slowest step in this whole chain. The amount of NO2 you form is what actually decides your ability to etch. So if you want to increase the etching rate, this is the equation that you're looking at. Okay, this is the equation that you should be focusing on. This is the rate limiting step. So as we discussed, this NO2 actually gets reduced to form NO2 minus ions. So this we have seen in the previous slide. And finally, this NO2 minus reacts with the hydrogen ion from the ionization reaction to form HNO2. Now, if you have keeping track, you would realize that we started with one HNO2 molecule, but we ended up with two HNO2 molecules. Through this whole mechanism, HNO2 is just participating as a catalyst. In fact, it is what we call a self-generating catalyst or self-regenerating catalyst. It's sort of a chain reaction. Even if you have one molecule of HNO2, if you give the solution enough time and something to react on or something to oxidize, the system will automatically generate more HNO2, which will enhance the oxidation ability of the HNO3. So where does the HNO2 come from? Maybe the first molecule comes because of impurity or because of random perturbations, but even once one molecule forms, after that, the mechanism itself generates its own HNO2 to further catalyze its own self. Okay. So HNO2 is thankfully spontaneously generated. We don't have to worry about it. It's not something we have to explicitly add. However, this does create an interesting issue that sometimes the HNO3 solution is not active from the get-go. So you pour HNO3 from the bottle into your beaker, you put your wafer, you start the reaction, but if you are doing the experiment very carefully, you might notice that for the first little bit of time, the etch doesn't work so well. And the reason for that is there is an induction period. It takes a certain amount of time for this oxidation reduction reactions that we discussed in the previous slide to happen, and for enough HNO to actually regenerate. And till that time, the reactant seems to just be standing still and doing nothing, but if you just wait it out, then you will see them becoming active again. If you are doing very shallow etches, if you are doing very careful etches where you cannot tolerate the induction period, or you cannot tolerate the variability that is introduced by this induction period, you can always choose to add some ammonium NH4NO2 into the solution. Okay? So, I think this is called ammonium nitrite. And what this does is it provides you with the NO2 minus immediately without you needing to regenerate it, and thereby avoid the induction period completely. So, well, that tackles the first part of the equation. Where is the NO2 coming from? Well, NO2 is coming from by spontaneous reaction between HNO3 and HNO2. Where is HNO2 coming from? HNO2 spontaneously generates HNO3 even if there is there is no HNO2 in the system to start with. The simple fact that you are doing an active reaction in the system will ultimately lead to some HNO2 getting generated, and then that will facilitate its own reaction. It will auto-catalyze itself. However, that still leaves the need or the argument for acetic acid open. We still not answered where in this whole scheme of things is acetic acid playing a role. So, for that, let us go to the next slide. Now, instead of giving you the answer directly, let me first pose a question. So, what is acetic acid a substitute for? I said acetic acid is a diluent or a solvent. So, strictly speaking, it is a substituent for water. We could have done this HNH in water. In fact, you can, a version of HNH can be done in water instead of acetic acid. But here we are deliberately choosing to keep acetic acid. So, what is it about acetic acid that is different from water? I urge you to give it a couple of minutes and think about it, like what all things do you know about acetic acid that is different from water? The second bit of hint that I want to give you for you to think is oxidation is limited by the reaction in the red, right? In the previous slide, this was the reaction in the red, that the rate limiting step is HNO2 reacting with HNO3 to form NO2 molecules. So, given this and given this question, what is your guess? What do you think is the role of acetic acid? It turns out the role of the acetic acid is dielectric constant. So, the dielectric constant of acetic acid is only 6.15, it is an organic molecule, so it is relatively low. And if you compare this to water, which is a polar molecule, which is extremely high dielectric constant of 80. Now, what does dielectric constant do? Well, dielectric constant reduces the energy of ionization. So, in a more polar liquid like water, or in a liquid which has a high dielectric constant, you tend to ionize more. However, if you do the same thing in a liquid or a solvent where the dielectric constant is low, you tend to ionize less. Does that get you closer to the answer? It turns out if you look at the equations in the previous slide, you would notice that the first equation we dealt with was with the ionization equation. Now, if you do this HNaH in acetic acid instead of water, the reduction in the dielectric constant means that the ionization is also reduced. See, ionization is more more when the dielectric constant is high. There is more screening and hence easier to ionize. But when the dielectric constant is low, it takes a little bit more energy to ionize, so the ionization reduces. If HNO3 is not ionizing, then more HNO3 is now available to react with HNO2 to form more HNO2 and also form NO2. So, I remember we said there are two competing pathways. HNO3 can ionize, which is what it wants to do as a strong acid, or it can oxidize, which is what it wants to do because it is a strong oxidizing agent. But now that we have reduced the possibility, we have impeded the pathway of ionization, that means we are helping the pathway of oxidation, and since that is the rate limiting step, that enhances the etching rate. So, in general with acetic acid as the diluent, you get more etching than with water. It also is that acetic acid is less polar than water, which means that the surface energy is different. So, it tends to wet the surface of even hydrophobic silicon. I think it was during cleaning that we discussed that if you take a silicon wafer and you strip away its oxide, then the water doesn't stick to the surface very well, it just flows away. And that's one way you can actually tell that your oxide etch is complete. So that was hydrophobic silicon. So hydrophobic silicon is silicon that does not have SiO2. Now when you are etching silicon, you are going into this pathway where you are forming silicon dioxide, but then you are etching the silicon dioxide which exposes fresh silicon, and that fresh exposed silicon is now hydrophobic. So if you can do this whole reaction in a medium that wets the hydrophobic surface better, then you would get better performance, better uniformity, better etching. So it turns out acetic acid is one such solvent where it just wets the hydrophobic silicon, which is exposed silicon, better than water does. So those two reasons are the reason why you want to do this whole process in acetic acid and what? Water. Okay, moving on. Now suppose we are looking at a unique composition. So let's take an example. So supposing you are dealing with a composition that is 50% HNO3, 20% acetic acid and 30% hydrofluoric acid. Let me grab my pointer real quick. Where is this composition on this iso-etch curve? All right. So the way to find that is you have 50% HNO3, so you go to the 50% point and you draw a line exactly parallel to the tick mark. All right. So that is this line. Then you draw a line for the 20% acetic acid, which is this line. And then you draw a line for 30% hydrofluoric acid, which is this line. And if this iso-etch curve is well made, which this one is, all these 3 points meet at a point. This is the composition that is, so this composition is represented on this graph exactly at this point. Each point on this graph hence represents a unique combination of these 3 etchants. Okay? And at each point there is a certain etching rate. For example, at this composition the known etch rate is around 50 micron a minute. And if you notice, this composition is close to this contour, and that contour has a value written of 56. These values are in microns per minute. So you are very close to the 56 micron per minute point, so it's no surprise that the etching rate that you get is nearly 50. What these contours are telling you is that all the compositions that lie on this line have the same etch rate of 56 micron per minute. All the compositions on this line have the same etching rate, and that is 43.5 micron per minute. And as it is, you keep going down, so all the compositions along this line have an etching rate of 16.5 micron per minute, and etc. etc. Now the highest etching is achieved somewhere in this composition where you both have a lot of HNO3 and a lot of hydrofluoric acid, so that's not surprising. So very little diluent, lot of nitric acid, lot of hydrofluoric acid leads to a lot of etching. So the peak etching, this contour represents all the compositions where the etching rate is 470 micron per minute. So you can essentially go through a whole wafer in a minute. Now the other thing to notice is the dotted line and the solids. So if for roughly equal amounts of nitric acid and sulfuric acid, nitric acid and hydrofluoric acid, you may notice that the etching rates are slightly higher with acetic acid as the diluent instead of water. So for example, let's take the case here, right? So this is very close to the contour which gives you the etching rate of nearly 50 micron a minute, right? But if the diluent was water, you would actually have to look at the contours given by the dashed lines. So which is the dashed line this is closest to? This is closest to the dashed line, that is this one, right? This one. And that has an etching rate of only 38 micron per minute, which is around 20%, 24% lower than 50 micron per minute. And this is true of all compositions. With water, you are getting lower etching rates. With acetic acid, you are getting higher etching rates. So that is the great advantage of using acetic acid as the diluent. Let's keep digging a little bit more into this. Okay. So this is again the same iso-etch curve. I just removed the labels from the previous graph. And let's now discuss what is happening in each of the corners. So supposing you were to look at all those compositions where the acetic acid, where the nitric acid is very little. So for example, if you look at this blue line is parallel to this axis. It's parallel to the tick marks on the HNO3 axis. So it represents all the compositions where the amount of HNO3 is very little. So this point, so which is what, 2%, 2% of HNO3. So very little HNO3. On balance, the rest of the 98% is either hydrofluoric acid or acetic acid. Now, the thing that you may notice is that the contours, the solid angles, the solid lines that you are seeing are parallel to this. Put another way, all these compositions, right, all these compositions seem to have exactly the same etching rate, and that etching rate is given by this contour, which if you trace is exactly 16.5 microns per minute. So it almost seems like for the composition which has very little HNO3, it doesn't really matter how much HF you have, whether your HF is 60% or HF is 90%, you essentially get the same etching rate, right. So the etching rate is independent of hydrofluoric acid, but depends on HNO3, which is that if you were to shift this line from this 2% HNO3 to say 10% HNO3, suddenly you are parallel to this contour, and in this contour the etching rate is higher, but again independent of the concentration of hydrofluoric acid, your etching rate tends to depend more on the absolute concentration of HNO3. Now this shouldn't be very surprising to those of you who have seen this happen before. Remember, two equations need to happen in series. We need to oxidize and then we need to etch the oxide. In an equilibrium system, these two rates must be equal, right. So the total etching rate is equal to the slowest step etching rate. So the slowest step decides. When you have very little HNO3, what you are doing is you are always waiting on the silicon surface to get oxidized. The slow step is the oxidation of silicon, because there is very little HNO3 in the system, there is very little HNO3 to oxidize the silicon. And because of that, it doesn't matter how much HF you put in, because adding more HF will just make the etching of the oxide faster. But etching of the oxide is not the bottleneck. The bottleneck is oxidation of silicon. So that is why the etching rate strongly depends on concentration of HNO3, does not depend upon the concentration of HF too much. Similarly, you can look on the other side. Now this green line represents all those compositions which have very little hydrofluoric acid, for example say 4% hydrofluoric acid, right. The balance 96%, some part is HNO3, some part is acetic acid. And once again, if you look at this edge, and this edge represents the case where there is little bit of diluent, but most of it is HNO3, right. So this is say 90 to 70% HNO3. So for all these compositions, it seems that it doesn't really matter whether the concentration of HNO3 is 70% or 90%. For all those cases, the etching rate that you get is 5.75 micron a minute. If you change the concentration of HF from 5% to say 10%, this line shifts up, and now irrespective of how much HNO3 you put in, you get an etching rate of 16.5. Once again, the complementary situation. Your etching rate seems to be decided by the component that is least present in the system, in this case that is hydrofluoric acid. What is happening? Well, here you are always waiting on the silicon dioxide to get etched. The oxidation of silicon happens quickly simply because there is so much HNO3 in the system. But once that oxide forms, it is now waiting on the HF to etch. Only then more silicon can be exposed, more etching can happen. So here you are waiting on silicon to get oxidized because HNO3 was in scarce supply. Here you are waiting on the silicon dioxide to get etched because hydrofluoric acid is in short supply. Now that tells you actually a lot about which composition should you use for a given application. So you see, this contour shows you that you get 16.5 micron per minute, both at a composition which has very low HF but a lot of HNO3, but you can get the same etching rate even on this side where there is very little HNO3 but a lot of HF. Which one do you choose? Depends on the application. So because you are hereby limited by the ability of HNO3 to oxidize the silicon, all the idiosyncrasies of HNO3 as an etchant are going to affect you. For example, you might be sensitive to induction period here. HNO3 has a problem with induction period as we discussed, and the longer induction period here might, so you might get a longer induction period simply because HNO3 is in scarce supply. Because this surface is always waiting on the silicon to get oxidized, the surface of silicon that you get after the etch invariably is oxide free. Now, that can be an advantage or disadvantages depending upon what your application is. And finally, because there is no oxide on the surface and this is a system which has a lot of hydrofluoric acid, you tend to get surface roughening. And this is a concept I have now discussed 2-3 times already, both in cleaning and in etching of hydrofluoric acid, where I discussed that HF doesn't etch silicon, but it can micro roughen it. So, all the compositions that are in this corner tend to suffer from that issue. Okay. The other thing you can do is of course be in the green corner. In the green corner, you are always waiting on hydrofluoric acid to show up. So, you are always limited by the ability of the silicon dioxide to get etched. So, what are the things that, what are the characteristics that you can expect? Well, you can expect that the silicon you get from these compositions will have a silicon dioxide layer on top of them, right, because they are always waiting on the silicon dioxide to get etched. So, any given moment in time, there is always some amount of silicon dioxide there. Typically, that thickness is around 3 to 5 nanometers. Now, that can be an advantage or a disadvantage. It turns out because of this passivating silicon dioxide and very low concentration of HF, you do not tend to roughen up the surface. So, here you roughened up the surface, here you do not tend to get roughen up surfaces. So, because you do not do roughening, you tend to get much more smoother, planar etches, and that is useful if you want a polished finish. If you want to remain in the middle, where you have both a lot of HNO3 and a lot of HF, you are in sort of no man's land. It is very insensitive to diluent, very little small changes in concentration cause huge jumps in etching rates which are very hard to control, and that is why this red zone is actually seldom used. You want to either be in the blue zone or in the green zone. Which one do you select? Depend on your application. For applications where you want a bare silicon, you do not want silicon dioxide, you may want to go with blue. For applications where you want smoother surface finishes, you may want to go with green. So, with that we come to the end of the HNA etch part. Let us now do some discussion on anisotropic etches of silicon, which are also very important and large class of etching. So, what is anisotropic etch? So, we discussed this in the first lecture on wet etching, where when you want to do etching that is dependent on the various facets or orientations of silicon, so it is not uniform in all the directions. So, for example, the anisotropic etch of silicon 100 often gives you these slanting profiles which are at 54.7 degrees, and that is because the etch is such that it etches the 1100 surface very quickly. So, this surface, this vertical surface is getting etched very quickly, but the etching on the 111 surface is very slow. So, because the etching is very slow, it sort of the etching progresses here very slowly, here very fast. So, you tend to get these sloped type of cross sections. Now, why does this happen? You can typically you can understand this simply by understanding that during crystal growth, we talked about how 111 was the easiest and the most easiest orientation to make. That was because it was the most stable. So, that the same order applies just in reverse. Now, the etching rates of 100 tend to be faster than 110, which tend to be faster than 111. Now, one area where this is very useful is actually in MEMS, where you want to make mechanical structures of various size, say silicon cantilever. Towards the end of this course, we actually have a whole module on actual, like a lab visit where you actually see how a cantilever gets made. We will also discuss the cantilever in a little more detail down the line. But the fundamental thing that all those techniques require is the ability to do anisotropic etches, and wet anisotropic etches is just one thing in your library of unit processes. The shape that you get is very strongly dependent upon the properties of the material as well as the orientation. So, for example, if you were to now discuss the anisotropic etch of silicon 110, you would actually not get this triangular shape profile or a trapezoidal shape profile, you actually get a vertical profile. In fact, this vertical profile is exactly vertical, and this also is the exposed 111 direction. And some of these etches are very useful because in general it is very hard to get exactly vertical profiles in an etch, but here is an example of an anisotropic process that automatically gives you a completely vertical sidewall, which is very useful for microfluidic applications. Now, what are the various types of anisotropic etches that we have access to? Most of the anisotropic etches tend to be bases. So, the simplest one we can think of is potassium hydroxide. Now it is safe, it is non-toxic, it is cheap, it has all those good things going for it. It's a strong base, so it is very highly ionized potassium and hydroxide ions. The problem some of the more astute students may see is this is not compatible with CMOS processing. When we are doing cleaning, we talk so much about how to prevent alkali metal contamination, how to prevent sodium contamination, how to prevent potassium contamination, how sweat is bad, you should never touch the wafer, etc., etc. The ITRS requirement was very low amount of sodium and potassium and all of that discussion, right? And here we are using a chemical that explicitly has potassium contamination, which is why this process is actually not compatible with CMOS. CMOS is what Intel does. They would actually never allow this process inside their fab. But for MEMS fabs, where they are not interested in electronic devices, or at least electronic devices of the caliber that Intel makes, they are okay with use of potassium hydroxide. One example is silicon solar cells. For you as a researcher, or for you who are working in an academic fab, the thing to remember is why we cannot afford different fabs for doing CMOS processing and MEMS work. We should be able to afford different tweezers, beakers, hoods. You must try to segregate CMOS and non-CMOS processes as much as possible. Otherwise, you just have a soup where nothing works. So we discussed this in contamination policy, and I refer you back to that discussion. What is the typical etch rate you get of around 0.3 to 1 micron a minute for silicon 100? Very interestingly, this etch does not etch the highly doped P layers very fast. You would think this is an issue, but it turns out this is an advantage. We'll talk about this as an etch stop in a little bit later. The anisotropy you get in this process is very high. The etching rate of the 100 facet is around 400 times faster than the 111 facet. The etching rate of the 110 is around 600 times faster than the 111. So this is very high anisotropy, very high anisotropy. What do you use to mask a layer? So this is a potassium hydroxide, which is a base. During photolithography, you must have discussed developers. And chemically speaking, developers also tend to be bases, which means the photoresist dissolves in bases. And if you were to use potassium hydroxide on a photoresist, the photoresist would dissolve. So photoresist is not a good masking layer for doing anisotropic etching using KOH. Invariably, you tend to use some hard masks. So silicon nitride or silicon oxide are often used as masks for this process. How do you get the silicon oxide and the silicon nitride? So first you do a patterning of the silicon oxide or the silicon nitride using hydrofluoric acid, and then use that patterned silicon dioxide to actually do the patterning onto the silicon. The selectivity you can actually get in this process is also very high. The nitride, for example, the selectivity is 10,000:1. For silicon dioxide, the selectivity is 100:1. So just 100 nanometers of silicon nitride is enough to etch around 100 micron of silicon, right? So that's very deep. Typical recipe tends to be that you have some potassium hydroxide, some isopropanol and water. I will not get into the detail of what the isopropanol does here. It's not part of a basic course really, but we do this at little higher temperature and under agitation. I urge you to go and look up under what conditions the anisotropic etches become more probable, and you will see that these satisfies those conditions. Finally, these etches tend to be fairly long. Sometimes you want to etch very deep structures, which takes a long time, hours. So during those hours, you don't want the concentration of your etchant to change too much. So often this etching is done in a closed container where the etchant just does not evaporate away. So at 80 degrees C, if you are keeping things for a few hours, you can imagine most of the water will just evaporate. So you have to prevent that from happening. Now, for those of you who do want to make a CMOS compatible anisotropic etch, there is good news. So KOH is not the only game in town, it's just the cheapest one. If you do want to do something that is CMOS compatible, you can use tetramethylammonium hydroxide. The structure is very similar. Those of you who are a little better at chemistry can imagine that this is nothing but a derivative of ammonium hydroxide. So ammonium hydroxide has this nitrogen and then 4 hydrogen. Here all that we have done is substituted the hydrogen with methyl groups, and then we have tetramethylammonium hydroxide. This is actually a very strong base, and this does the same job that KOH does chemically speaking. It provides OH minuses which actually do the etching. The advantage is there is no alkali, there is no sodium, there is no potassium, so this is CMOS compatible. In fact, developers that are metal ion free, which are compatible with CMOS processing, actually use TMAH as a base, not as potassium hydroxide. One problem that it does not, however, solve is that you still need a hard mask. You still cannot use photoresist because photoresist dissolves in TMAH. So, we typically have to resolve to hard mask like silicon nitride or silicon dioxide, but the selectivity is excellent, so there is no problem. The etch rate of this is around 1 micron per minute for silicon 100. This incidentally also stops at P plus layers, and we shall discuss that later. The anisotropy compared to the KOH bit is a little lower. Between 100 and 111, you only have a factor of 10 or a factor of 35, not hundreds as previously. So, that is one disadvantage of TMAH, but then again it's CMOS compatible. The typical recipe typically is dilute TMAH at 90 degrees C under agitation. Once again, these etches tend to be long, so you must cover them, otherwise the etching concentration changes, and so does the performance of the etch. Now, what is the underlying mechanism? Both the hydroxides, KOH or TMOH, functionally do the same thing. They provide the OH minus, which reacts with silicon to form a complex, and that complex goes away. It forms a soluble complex that goes away. Now, why does it give you anisotropy? Why is this reaction different on different facets? Fundamentally, this is an oxidation reaction. So, what is happening to silicon that you are etching is that it's getting oxidized, and at the counter domain, something is getting reduced. What is getting reduced? In this case, water. It so turns out that the rate at which the silicon 111 plane oxidizes is much faster, and what that does is it forms a silicon dioxide layer, and that silicon dioxide layer then protects the underlying silicon 111, thereby reducing the etching rate. But the silicon 100 does not have that protective oxide, so it continues to dissolve, and thereby you get etching only in the 100 direction, but the 111 direction continues to remain protected. Now, what is the proof behind this mechanism? The proof behind the mechanism, at least anecdotal proof or circumstantial evidence, is that if you look at the etch rate of the silicon 111 in TMAH, it's 8.5 nanometers a minute at 85 degrees C. A very low number. And this is exactly the same etching rate that you would get if you were to etch silicon dioxide that has been grown on the silicon 111. So, this etch rate being equal to this rate strongly suggests that the slow step that is preventing the etching of silicon 111 is actually the passivating oxide, is actually the removal of the passivating oxide. So, with that we will actually, I think, end the discussion on the mechanism. We shall now discuss a little bit of practical detail on how do we actually implement this in an actual MEMS system. So, the fact that anisotropic films give you different shapes or different cross section, it has to be understood a little bit better so that you can utilize it in your MEMS devices. So, what the shape you actually get depends upon, of course, the anisotropy of the agent, TMAH versus silicon KOH versus HNA, but also on the etch time, mask pattern, wafer orientation, and etch stops. Now, these last four are not obvious, and through examples I would like to highlight each of these. Let us first take the concept of the etching time. Now, supposing after lithography you got this pattern, right. So, you had a silicon 100 wafer, you have a hard mask which is silicon dioxide. It's protecting the backside completely, so there is no etching happening there. On the front you have opened a little hole, this exposed area is 100, and this system is now put in an anisotropic etch like KOH. So, it will start etching. As you keep the system in KOH for longer and longer, this system will continuously etch, and ultimately you will reach a point where the 111 planes touch. At this point there is no exposed 100 area at all. If there is no exposed 100 area, the etch slows down to a crawl. If you keep the system in the solution for longer, you will get some etch, because even the 111 is also etching at 8.5 nanometers a minute, but very slowly. So all you will get is you will get an undercut the longer you keep it, a little more undercut the longer you keep it, but the shape will not change anymore, the shape will maintain itself because you are exposing 111, which is the slowest etching facet. So this is what is called a self-limiting etch. This is what happens for small openings and long etching times. Now supposing you were to increase the size of the opening to make it a little larger, and now put the same system again in the etching solution. So for the same time that you got to a self-limiting behavior here you would not reach the self-limiting behavior, because you would get these facets which are 111, but you would still have some exposed 100 which continues to etch. Now as you keep this longer, this 111 facet will continue to become larger and larger. Ultimately it reaches this pinching point where once again you have now run out of all 100. So there is no 100 facet to be seen. So now from this point onwards, the etching rate is only happening on the 111 surface, which is very slow. So you have a self-limiting etching. If you keep it very long, you will get some undercut, but the shape will not change. So this is the example of etch time, which is the y-axis here, and the mask pattern. Depending on whether it's a small opening, the large opening, you actually get either a feature that looks like a trapezium or a feature that looks like a triangle. And of course, there is a wafer orientation. I am doing all of this in silicon 100. A couple of slides ago, I showed you that the cross section of 110, which was vertical, looks very different. The final example I would like to discuss is supposing you had a very large hole on the back side. And these are often used for cases where you want a through hole, a hole that is across the whole of the width of the silicon wafer. Now those of you who are interested in geometry may have noticed that the depth of this self-limiting etch is some trigonometrically related to the opening that you need. So if you want to etch 400 micron, this is an assignment question, you can probably calculate what sort of opening do you need. So if you give that large an opening, then you have a possibility of etching a through hole, one that does not do self-limiting etching for the whole thickness, right? So in that case, what will happen is for some time you will etch some distance, if you keep it longer you will etch further, but if you keep putting it for a very long time you will actually go and hit the silicon dioxide on the other side. Now you have an exposed 111 facet which is etching very slowly, and a silicon dioxide which etches even slower. So now you are in a self-limiting regime, but now what you have is a through hole. If you etch the silicon oxide away, you have a hole through the silicon wafer, which is often used for various applications. Whatever we just discussed can also be interpreted from these figures. I got these figures from this very nice paper, which is actually an open access journal. So I urge you to go and read it. So for example, if you had a silicon 100 wafer, this major flat in the 100 wafer is actually the 110 direction. So supposing you had a circle. So if that circle is aligned such that the square that transcribes that circle is parallel to the 100, so this direction then is 110, and this direction is also 110. So if you were to do the etching on this, what you would actually get is you would get these slopes. So imagine in 3D, right? So these are slopes, and if you look at the cross section of this line, which is AA star, so this is the AA star cross section. So you actually get that 54.7 degree slope, and then a flat which represents the 100 plane. So this gray is the 100, the green is the 111. So it doesn't really matter whether you made a circle or a square or some arbitrary shape. You in all cases will actually etch these rectangular looking features on the 100 wafer, right? So mask design matters. It mask design matters. If it doesn't really matter what sort of mask you have, you always get these rectangular features. And if the size is very small, then of course you get self-limiting etching where you don't have any exposed 100. Okay. Another example, let's talk about the anisotropic etching of silicon 110. So this is the 110 wafer. So in this case, the major flat is also the 110 direction. But now if you look at more closely, if you have a circle, you have major flats which is 110. This is a 112 direction, this is a 112 direction, this is 110 direction, this is again a 112 direction. If you do this etching, anisotropic etching on this wafer, things are a little more complicated. So, in order to understand that, let us take two cross sections. One is this A double dash cross section, which looks like this. So, this is very similar to what we had in the 100 case, where you have these sloping boundaries which represent the 111 direction, and this base, flat base, which is the 110. So, the gray is the 110, the blue is the 111. However, you see that the angle is different, and that is because the angle between the 100 and 111 and the angle between 110 and 111 are slightly different. The angle between these two is 35.3. But there is another cross section that follows, and that is this gray and orange bit, which is the BB double dash, and the BB double dash cross section looks like this, where the walls are exactly vertical. So, these exposed facets are 111, and if you, this is an example of absolutely straight vertical lines. So, this anisotropic etch gives you completely flat and 90-degree channels, something that is very hard to do unless you are doing dry etching. But simply because you are playing with anisotropy and you are playing with the right facets, you can actually get these very vertical channels very nicely, very useful for microfluidics type of applications. With that, we came to the end of the portion on anisotropic etching of silicon. We shall take a break here. In the next lecture, we shall continue on the anisotropic etching of other materials, specifically gallium arsenide. We shall look at a general class of anisotropic etchants which are used to delineate defects. So, those are called defect etches. And we will also look at some process integration issues of how we put all of this together to form a silicon cantilever. As I mentioned, the lab visit for that will come later. So, we will discuss it theoretically now, and you can then correlate with what you see in the lab later. So, see you then. Thank you.